Hi Wildcats. I wanted to make a video today that went through some of the things that we've talked about in class, specifically free body diagrams, net force, but then we've also introduced now what happens to forces when an object is at an angle. Okay, so we're going to go through two problems here. I'm on these scales. These scales are not normal scales that give us our readings in um, kilograms, they are going to be normal force scales. So when we get on there, it's going to actually give us the reading in normal force. Okay, so it's a fancy physics scale. Uh, so my question is, what are these scales? How would they be different? If these are the normal force scales, how will they read? Will they read different when I am on a flat surface when I am on an angled? And what would those be? So let's figure that out. Okay, so um, I've told you my mass is 91.7 kilograms. So I guess let's figure out what the mass would be when I just stand on the scale on the flat ground. So first, let's draw a free body diagram. Okay, so there's me, and we're going to have the force of gravity, and then there's also normal force, and we said that these will be equal but opposite. And we said normal force in this scenario is just equal to the opposite of the force of gravity. So mathematically, we could say normal force is equal to the opposite of the force of gravity, and force of gravity is so opposite of the force of gravity, and force of gravity can be defined as mass times acceleration due to gravity. They don't tell us we're on some other planet, so we'll assume this is Earth. So in this case, the normal force will be the opposite of 91.7 kilograms times 9.81 meters per second squared down. So negative times a negative, I'm going to end up with a positive answer. That's good because my normal force arrow points up. So 91, put that on my calculator, 91.7 times 9.81, negatives cancel. So 8.99.577, we'll just say for the sake of argument that my weight is 900 newtons up. Okay, so if my mass is 91.7 kilograms, this scale is going to read 900 newtons. I'm going to put this over here. This scale reads 900 newtons. Okay, what will this scale read? All right, so that's a little different because one thing we talked about in class is that I'm going to draw the forces on here, is that for now, and then we'll make a free body diagram. The weight is always straight down towards the center of the earth. So my weight is going to be this. Okay, so this is normal force. And we also said when we define normal force that normal force is always perpendicular to the surface. So if this is the surface, then the normal force is this, right? Okay, so that's what we're working with. And the problem is that if this is normal force, unlike over here where it's nice and easy and they're equal but opposite, these are not directly opposite, right? They're not parallel to each other because normal force is at an angle here. So that presents us with a little bit of a problem. So I'm going to transfer these to a nice free body diagram that we can easily work with. So here is the force of gravity, and then my ramp can be right here. So therefore normal force would be here, and this is 20 degrees. Okay, so things that we know. Well, my weight hasn't changed, right? I've not, assuming all things being equal, my weight is still 900 newtons when I'm on this scale. Okay, I haven't eaten anything, nothing in, nothing out. So I'm still 900 newtons. So one thing I know over here is that my weight is still 900 newtons down. The question is, will that scale read 900 newtons up like it did over here? Okay, so to figure that out, we said it's not equal but opposite. So what will it be? Okay, so the key to this is we actually want to rotate our picture. And so if you have a sheet of paper and you're working on paper, you can just rotate your paper. This doesn't quite work that easily, so I'm just going to redraw this. And I want to draw this so that my normal force is straight up. Okay, So you turn your paper to the left, so normal force was pointing straight up. And when I turn the paper, right, so imagine I'm turning this whole paper this way, that means that normal force is going to rotate to the left, and the force of gravity is going to rotate to the right. So now my force of gravity is over here. Okay, so this is Fg. So I'm just redrawing this. Now, if you took out a protractor as you turned your paper and rotated your paper, you would see that we are turning the normal force this direction and we're turning it 20 degrees. So I'll spare you the math proofs, but in order for our normal force to get from here to here, we have to turn it 20 degrees, which means that then this, our force of gravity, also rotated this 20 degrees. And so if I redraw this line over here, this angle is now 20 degrees, okay? Because the force of gravity was here where this dotted line was when it was straight down, and I rotated it to the right. How far? Well, I rotated it to the right 20 degrees. And if this ramp was a 45-degree ramp, then all those angles would be 45. Okay, so that's nice and easy, is that whatever the angle the ramp is, if I'm rotating my paper, I'm getting that same angle right here. Okay, so now I can see that this force of gravity has a y component. So this dotted line I just drew is its y component. And this dashed line over here is the force of gravity's x component. So we have chosen to turn their paper, which when we get to friction, you'll see why, and break force of gravity into its two components, its y component and its x component. And if I look at this, right, all the forces, this object, I am on the scale, I'm not moving up and down, and we're assuming I'm not sliding up or down this ramp, which means the vertical forces have to be equal but opposite. So what we can say is normal force is equal to the opposite of the force of gravity, but not all of the force of gravity, only its y component. So if I can figure out the force of gravity's y component, or this right here, I can take the opposite of it, and that would be normal force. So this is just going to be trigonometry. Okay, so I'm going to move this over here, give myself a little bit of room to work. I'm going to redraw this triangle so I have a nice big picture to work with. You can see, so this is the force of gravity. We said the force of gravity is 900 newtons down. And this is Fgy, the y component of the force of gravity. This is Fgx, and this is 20 degrees. So I've just taken this vector and moved and drawn it down here. So in this case, Fgy is adjacent, right? This is the adjacent side of my triangle. So if I'm using SOHCAHTOA, I want the one that has adjacent in it, and that is cosine. So I would say or I guess, let me start that over. I would say cosine of the angle is equal to adjacent. So what's adjacent? Fgy divided by the hypotenuse, which is the force of gravity's, the resultant or force of gravity. So to get Fgy, just multiply both sides by force of gravity. Oops, don't. Over 1. Multiply this by force of gravity over 1. Those cancel. Force of gravity's y component is equal to the force of gravity times cosine of theta. Okay, so if I look at my picture here, force of gravity is negative 900 newtons times the cosine of my angle here is 20 degrees. So force of gravity, y's component, or the y component of the force of gravity, is the cosine of 20, gives me 0.939. Take that times negative 900, and I end up with negative 46 rounding newtons. So 846 newtons. And if I come up here, we said the normal force on this scale is equal to the opposite of the force of gravity. So if force of gravity's y component. So if the force of gravity's y component is 846 newtons down, in other words, this line right here is 846 newtons down, this has to be equal but opposite. So therefore, the normal force in this problem is equal to 846 newtons. So the scale would read a smaller number. And it would seem like I lost weight. Now we know that there's a difference between mass and weight, right? So I haven't lost any mass. It's just that I'm getting a different force reading because not all of that force is now straight down. Some of that force is on an angle in the x direction. And so if you're looking at this picture, some of you might go, wait, now this object does not have a net force of 0 because force of gravity has an x component, right? There's some force horizontally to the right. So this force is a force. FGX is an actual force. And so if I were to put that up here, right, that would be going this direction, right? Pulling me down the ramp. And so now there is some force. This is FG's, the force of gravity's X component. And that's what pulls me down the ramp. If I'm not moving, that must tell us that there is some other force in this direction. Okay, so there's some force here preventing us from sliding down, because if we're going to say F net is 0, then there is no motion up, down, left, right. Now we see that normal force and the force of gravity's y component are equal but opposite. So therefore, these must be equal and opposite. The question is, what is this force? And that's where we're going to go to next. This is the force of friction. Okay, and they would be equal and opposite. And so we'll get there. That's the next topic we're going to cover. So you can see how we're going to get there. But in this part, hopefully you can see how we can resolve for the vertical or determine normal force when we're told information about the force of gravity. And we can see why the scale would give me a less number even though my mass hasn't changed. And that's because not all of this force of gravity is pulling me down. Some of it is pulling me sideways now as well. Okay, so hopefully that helped as we work through this problem. These are the types of questions that you should be able to do for your quiz, as well as the labs that we'll be doing coming up and determining normal force of objects on an angle, as well as when they are on a nice flat surface. I hope this helps.